Hello, everyone. Welcome to our Deep Dive podcast, where today we'll be reviewing the paper ZonUI-3B Competitive GUI Grounding with a 3B VLM trained on a single consumer GPU.
Are you ready to explore the world of lightweight vision language models for GUI grounding? Absolutely. This paper is quite exciting, especially since it claims to achieve state-of-the-art GUI grounding performance with just a 3B parameter model, all trained on a single RTX 4090 GPU. That's impressive, isn't it?
It really is. Let's start by clarifying what GUI grounding means. In this context, it refers to the task of locating the correct user interface element on a screen, given a natural language instruction. This is a foundational capability for building intelligent GUI agents.
Right, and traditionally, large-scale vision language models, often with over 7 billion parameters, have dominated this task. But their training requirements are so high that they're out of reach for most researchers and practitioners.
Exactly. That's why there's growing interest in compact models that can still deliver high accuracy. ZonUI-3B is a response to this need. The authors introduce several innovations to make this possible.
Let's break down those innovations. First, they constructed a cross-platform, multi-resolution dataset of 24,000 examples. This dataset includes mobile, desktop, and web GUI screenshots. Why is this important?
Because existing datasets often lack diversity, especially in high-resolution desktop environments. By combining data from multiple sources, they address data scarcity and improve the model's ability to generalize across different platforms and resolutions.
The second innovation is their two-stage fine-tuning strategy. In the first stage, they train the model on a mix of platforms to establish robust GUI understanding. In the second stage, they fine-tune it on high-resolution data to enhance adaptability. This staged approach is quite clever, isn't it?
Yes, it is. It allows the model to first learn general GUI semantics and then specialize in handling complex, high-resolution layouts. This is crucial for real-world applications, where interfaces can vary widely.
The third innovation is their approach to data curation and redundancy reduction. They found that randomly sampling a smaller, less redundant subset of data achieves performance comparable to using the full dataset. This emphasizes the importance of data diversity over sheer volume.
That's a key insight. Training on a compact, diverse dataset not only saves resources but also maintains high performance. Now let's talk about the model architecture. ZonUI-3B is based on the Quotient 2.5D GL3B backbone, which is designed for efficient multimodal understanding.
This architecture supports dynamic input resolutions and multi-scale visual features. It also includes native support for absolute coordinate grounding, which is essential for GUI element localization.
To adapt the model for the GUI grounding task with minimal computational overhead, they use low-rank adaptation, or LoRA. This technique introduces trainable low-rank matrices into frozen transformer layers, reducing memory usage and training cost.
And importantly, LoRA parameters can be merged after training, so there's no additional runtime latency. The model processes raw GUI screenshots and natural language instructions without relying on auxiliary inputs like HTML structures or OCR modules.
That's right. The simplicity of the architecture makes it easier to analyze the effects of training strategies and dataset composition. Now let's discuss the two-stage fine-tuning strategy in more detail.
In Stage 1, the model is fine-tuned on a mixture of GUI data from mobile, web, and desktop sources. They use a class-balanced sampling scheme to ensure uniform exposure across device types, especially since desktop data is often underrepresented.
The goal here is to establish a general understanding of common GUI components and natural language instructions across diverse environments. Then, in Stage 2, the model is further adapted using high-resolution screenshots, primarily from uGround's Web Hybrid dataset.
This dataset introduces a variety of screen resolutions and aspect ratios, simulating different device-specific web renderings. The aim is to improve robustness under dense visual conditions and interface variability.
Importantly, the model architecture remains unchanged throughout both stages. This two-stage schedule yields consistent gains in grounding accuracy, especially for desktop and web platforms.
Now let's talk about the training pipeline. The authors emphasize simplicity, data efficiency, and computational accessibility. Unlike other frameworks that introduce complex architectures or require massive datasets, ZonUI-3B relies on standard supervised fine-tuning.
For example, UI-TARS incorporates system-level reasoning modules and reinforcement learning-based data collection, which increases complexity and resource requirements. uGround uses over 1.3 million screenshots and 10 million annotated elements, requiring extensive data curation.
In contrast, ZonUI-3B uses just 24,000 carefully selected examples. This compact design improves training efficiency and lowers the barrier for reproducing or extending the model.
Compared to ShowUI, which also targets lightweight GUI grounding, ZonUI-3B further simplifies the pipeline by avoiding custom architectural changes. ShowUI introduced a UI-guided token pruning module, but ZonUI-3B benefits from the resolution diversity of its dataset.
The training process is minimal, fine-tuning a 3B backbone using LoRa-based adaptation and gradient accumulation on a single RTX 4090 GPU. No auxiliary modules or external tools are needed.
This demonstrates that effective grounding performance can be achieved through careful data construction and staged adaptation, without scaling up model size or pipeline complexity.
Now let's move on to the experiments. The authors conducted their experiments using a single NVIDIA RTX 4090 GPU with 24 GB VRAM. They used DeepSpeed ZR02 optimization and flash attention to reduce memory overhead.
Fine-tuning was performed using LoRa with rank 8 and alpha 16, applied to selected transformer layers. Mixed precision training was used throughout, with a batch size of 1 and gradient accumulation steps set to 48.
Training was performed in two stages, as we discussed earlier. In Stage 1, the model was trained on a mixed dataset of web, mobile, and desktop GUI screenshots, with a learning rate of 2E4 and balanced sampling.
In Stage 2, the model was further adapted on a high-resolution subset from uGround's web hybrid data, with a reduced learning rate of 5E5 to stabilize fine-tuning on dense visual inputs.
Evaluation was conducted on 3 GUI grounding benchmarks: ScreenSpot, ScreenSpot v2, and ScreenSpot-Pro. Each benchmark comprises 1,272 natural language grounding tasks paired with GUI screenshots from various platforms.
Success is defined by whether the predicted coordinates fall within the annotated bounding box. ScreenSpot v2 improves upon the original benchmark by correcting annotation errors and clarifying ambiguous instructions.
ScreenSpot-Pro targets professional, high-resolution interfaces with full-screen layouts from tools like Photoshop, AutoCAD, and MATLAB. It features smaller UI targets and more visually complex scenes.
Now let's look at the main results. On ScreenSpot, ZonUI-3B achieves an accuracy of 84.9%. On ScreenSpot v2, it reaches 86.4%, setting a new benchmark among all sub-4B models.
Compared to the previous best 2B scale model, UI-TARS 2B, ZonUI-3B yields a 2.6% gain on ScreenSpot and 1.7% on ScreenSpot v2. These results indicate that the training strategy and dataset design effectively close the performance gap between small and mid-sized models.
Beyond sub-4B models, ZonUI-3B performs on par with several 7B scale systems, such as Aguvis 7B and OS Atlas 7B. This suggests that, with proper adaptation and data curation, a 3B model can achieve competitive performance typically associated with much larger models.
On ScreenSpot-Pro, which is a challenging benchmark, ZonUI-3B achieves a success rate of 28.7%. This surpasses the strongest prior 2B baseline and exceeds several 7B models, further validating its robustness in high-resolution, real-world applications.
These results establish ZonUI-3B as a strong candidate for GUI grounding under constrained resources. The model demonstrates that with a compact architecture and carefully designed training strategy, it is possible to attain competitive accuracy without relying on extensive model scale or massive datasets.
The authors also conducted ablation studies to evaluate the effectiveness of individual components in their training pipeline. They focused on sampling strategies, dataset composition, and the two-stage fine-tuning schedule.
To address the imbalance in GUI data across platforms, they compared uniform sampling with joint training that reflects the original data distribution. Balanced sampling yielded a modest improvement in overall accuracy and a slight gain on desktop-specific performance.
This suggests that balancing platform representation during training can help stabilize performance on underrepresented high-resolution interfaces.
They also evaluated the trade-off between dataset size and diversity. Simply scaling up the number of samples led to negligible gains in overall accuracy. In contrast, merging datasets to increase diversity improved performance.
This finding aligns with their observation that existing GUI datasets contain considerable redundancy, and that well-curated, compact subsets can offer equivalent or superior results.
The impact of the two-stage fine-tuning strategy was also significant. Adding multi-resolution data from uGround to a small ShowUI subset yielded minor improvements. However, applying two-stage fine-tuning resulted in substantial gains on desktop and web interfaces.
This confirms that separating general GUI pre-training from resolution-specialized adaptation is a key factor in improving grounding accuracy, particularly on visually complex layouts.
The ablation studies validate the effectiveness of the training methodology. Rather than relying on large-scale data or complex architecture modifications, performance can be significantly improved through targeted sampling, dataset composition, and phased training strategies.
Now let's discuss the broader implications of this work. ZonUI-3B provides a practical and reproducible strategy for building deployable GUI agents. It shows that model compactness need not compromise grounding performance.
The study affirms that targeted design choices in data construction and training schedules play a critical role in maximizing capability within constrained computational budgets.
By integrating a compact yet diverse dataset and applying a two-stage fine-tuning strategy, ZonUI-3B achieves state-of-the-art performance among sub-4B models and rivals several 7B scale baselines.
Importantly, this is accomplished using a single consumer-grade GPU without introducing architectural modifications or external modules.
The results also highlight the importance of data diversity, platform balancing, and resolution-aware adaptation. Increasing data volume alone yields diminishing returns, while a small, well-curated dataset can maintain or exceed the effectiveness of much larger corpora.
The proposed training framework enables robust grounding even in high-resolution and visually dense desktop environments, which have traditionally been a weakness for lightweight models.
ZonUI-3B's approach to data curation, redundancy reduction, and staged fine-tuning sets a new standard for efficient and effective GUI grounding.
Before we wrap up, let's briefly touch on the references and related work. The authors compare their approach to several recent models, including UiTARS, uGround, ShowUI, OS Atlas, Agavis, and others.
Each of these models has its strengths, but ZonUI-3B stands out for its simplicity, efficiency, and competitive performance, all achieved with a much smaller computational footprint.
The use of LoRa for efficient adaptation, the focus on data diversity, and the two-stage fine-tuning strategy are key differentiators.
The open-source release of ZonUI-3B and its resources also makes it accessible for further research and practical deployment.
In summary, ZonUI-3B demonstrates that with careful data selection, efficient training strategies, and a compact model architecture, it is possible to achieve state-of-the-art GUI grounding performance on a single consumer GPU.
This work paves the way for more accessible and deployable intelligent GUI agents, making advanced vision language capabilities available to a wider range of researchers and practitioners.
That concludes our review of ZonUI-3B. Thank you for joining us on this deep dive into efficient GUI grounding. We hope you found this discussion informative and inspiring.
Absolutely. To summarize, ZonUI-3B achieves competitive GUI grounding performance with a 3B parameter model trained on a single consumer GPU by leveraging a diverse, compact dataset and a two-stage fine-tuning strategy. setting a new standard for lightweight, efficient vision language models.
Thanks for listening, and we'll see you next time for another in-depth paper review.